Dear friends, welcome to this Electrical Engineering Knowledge Sharing channel, AMP Power System. We are discussing the short circuit calculation for three-phase electrical network under session 7. In this session, we have already completed 4 videos, 3 videos for the symmetrical short circuit calculation, and the 4th videos we have started the basic module for the calculation of asymmetrical fault current. Out of that, we have already discussed about the sequence component for the voltage and current, and the balance is the sequence component for the impedance. So to discuss about the sequence component of impedance, we have classified the load under 4 categories. One is a non-rotating equipments, one is a rotating equipments, one is transmission line, and the fourth one is a transformers. Out of this non-rotating equipment sequence impedance network, we have already discussed under video number 59, and that is completed. Now the rest of the sequence impedance for the rotating equipments, transmission line, and the transformers will be covered under this video. So let us start the video. This video number will be 59. Let's start this video number 59. So in case of rotating equipment, first we will discuss rotating equipment, then we will go for the transmission line, transformers, and finally we will go for the transmission lines. Now for the rotating equipment sequence impedance, we will be developing the same way as that of non-rotating equipments. Only difference in the case of rotating equipment like generators, in the network there will be voltage source, because generator is producing voltage unlike to the other loads. So that voltage source will be present on each phase of the generators. And second difference is, in the case of generator, it will be producing power outside. It will be producing power to outside. In case of load is taking power from outside to inside, and it will giving power from inside to outside. The direction of the current flow will be different. So let's draw first the non-rotating equipment, how we develop for the star connected non-rotating equipment. We have seen, like this is our non-rotating equipment network. That was the network for us. That was a VA, VB, and this was a VC, right? And the star was connected by a ZN. And we have said this is ZY, this is a ZY, and this is ZY. We have seen that sequence network how much? Z0, that is a zero sequence impedance for this. ZY plus 3ZN, that is the zero sequence. Positive sequence was ZY, and that is also Z2 is also ZY. The positive and negative sequence was equal. Zero sequence impedance was phase impedance plus 3 times of ZN. We have seen this relation. And from this, what we calculated? We have calculated the sequence relation between sequence impedance, sequence current, and sequence voltage. That is a V0. That is, we get Z0 ZY plus 3ZN into I0, and V1 that equal to ZY into I1, and V2 negative sequence voltage equal to ZY into I2. We got this. From this, we have developed the sequence network. That sequence network we have seen in the zero sequence network. This will be like this. This is a ZY, this is a 3ZN. The current is flowing I0, and this is a voltage source V0. For the positive sequence, how it was? It was like ZY. It is a current is flowing I1, voltage source is V1 over here. And for the negative sequence, is same like positive sequence. This current is flowing I2. This is a ZY, and this is your V2. We have seen this thing in the video number 58 for the non-rotating equipment. Maintaining the same way, only when you go for the sequence network for the rotating equipment, what will be the difference? Difference will be, instead in this network, in this topology, we have to add a voltage source. There will be a voltage source on each phase. That means there will be a voltage source over here. There will be a voltage source over here. There will be a voltage source over there. If this voltage source is VG, you say this is VG, means generator. Then this will be negative, this will be positive. Okay. Then similarly positive, negative. This is a positive, positive. This is a negative. Okay. This is negative, positive. And the current is going outside. This is a suppose this is IB, this is IA, and this is IC. And the neutral current we know IN equal to how much? That is equal to IA plus IB plus IC. Now this voltage source, this is the only difference. But we have to keep in mind the generator is always producing a positive voltage, positive sequence voltage. It never produces any negative or zero sequence voltage. So in this network it is there, but when you go to the positive sequence network, zero sequence network and the negative sequence network, voltage source will be present only in the positive sequence network. Zero sequence network or negative sequence network does not produce any voltage source. So with this we can develop similarly this impedance network, impedance with ZS. We can develop the sequence impedance that equal to how much? Z sequence impedance means Z0, Z1 and Z2. This that is equal to same. How that will be? That will be zero sequence. How much? It will be, suppose this is a ZG. We are telling this is a ZG. For the generator we put ZG. Then it will be ZG plus 3ZN. And positive sequence will be ZG, negative sequence will be ZG. So this will be the single matrix. So Z0 equal to how much? This will be Z0. So it will be Z0 will be same like it will be ZG here. Z1 equal to same, it is ZG. Z2 is equal to ZG. And in the positive sequence network there will be a present of voltage source. So this calculation will be same like as we did for the rotating equipment. So I am not going to calculate that thing again. So that will be the sequence impedance for the rotating equipment. So what will be the sequence equation between the, what is the relation between sequence impedance, sequence current and the sequence voltage for the generator? We can develop very easily. We know V0 equals to how much? V0 equal to zero sequence impedance, that is how much? ZG plus 3ZN, right? That into I0. Positive sequence voltage equal to how much? ZG plus, we have said there will be a voltage source present over here, VG, that is a positive sequence voltage. And V2 equals to how much? That is equal to again ZG. There is no sequence voltage. So this is one of the difference over here. So if we develop the sequence network for this generator, then how it will be? Positive sequence network if we draw, zero sequence network if we want to draw for this rotating equipment. Zero sequence network means how will be? This will be the ZG. Suppose this is your ZN. Then there will be a voltage source VG. And then it will be coming over here. This is a positive, this is negative, right? So this is your ZG. This is your 3ZN. And current is going this way. It will be going, I0 will be going this way. Sorry, this is ZN. Sorry. There will be no voltage source over here. This is a directly connected. This is the zero sequence voltage. ZG, that is ZG plus 3ZN. Current is following. This is I0. Here is the voltage, this is V0. So that will be the zero sequence network for the generator. Then if we go to the positive sequence network, then how it will be? There will be a impedance ZG. Then there will be a voltage source over here, positive, negative. This is a VG voltage source. And then it is coming back. This is a V1. Power is going where? Outside, not inside. That is the difference between the load and the generator. So this current is a I1. So it will be same like a non-rotating equipment, only the generator is connected over here with the voltage magnitude. So this is the positive sequence. Now if we go to the negative sequence, same like, it will be same like here. That will be, that is your ZG. And then it is coming back, current is going I2. This is a V2. That will be the sequence network for the generator. Now in case of other rotating equipment like motors, induction motors, synchronous motor, it will be applicable in the same way. Only difference in the case of synchronous motor, sequence network will be same. But as it is a motor, so what it will happen? It will take the current instead of giving the current. So this direction of the current will be changed. In the case of synchronous motor, it will be like a synchronous generator, but the current direction will be inside. This will be I1 this way. Similarly, I2 will be going this way in case of synchronous motor. In case of induction motor, what will happen? Induction motor has no generating source. So in the positive sequence network, it will be like this. That means you can say other way, induction motor sequence network is similar to that non-rotating equipments. Is similar to non-rotating equipments. So these are the sequence network for the generators. Now we'll go to the sequence network for the transformer. We have already said transformer is slightly different from the other equipment. Why it is other equipment? Though it is a non-rotating equipment, however, transformer construction wise, it is a different, electrical construction wise, it is different from the other non-rotating equipments, because transformer has a two windings. One is a primary winding, another is a secondary winding. So if you see the transformer, how is it? Suppose there is a, we are considering there is a one transformer with a star-star connection like this, and neutral is connected like this. This is suppose primary side, HT side, and LV side, low tension side, there is a similarly there is another winding which is connected through neutral. Okay, if we consider this way, so these are the three. Suppose this is HB side, that means it is a VA, VA. Suppose this is a VB, and this is VC, and this is a suppose VX, this is a VY, and this is a VZ. You consider in that way, three phase. Okay, or it is a VX, VY, VZ, VA, VB, VC. Okay, or you can put a small a, VA, VB, and this is VC. This is primary. This is suppose this is your impedance. Suppose it is a ZA. All are ZAs, and it is your ZX, LB side impedance ZX. It is a Z small n, it is capital Z capital N. You consider in that way. That means transformer can be looked into as a two non-rotating equipments. This is one non-rotating equipment, this is another non-rotating equipment. So transformer is actually combination of non-rotating equipments. So each non-rotating equipment we can represent by its own network. So if we consider this is HB side, so HB side it has a positive sequence impedance, zero sequence impedance, and negative sequence impedance. We have seen already. So in case of star connected, zero sequence impedance how much? That equal to phase impedance plus 3 into Zn. We have seen it. And Z is, that is, this is equal to Z, suppose H0, high voltage side. This is equal to Z is equal to Z H1, and Z is that equal to Z H2, negative sequence impedance for the high impedance, high voltage side. Similarly, low voltage side, it will be same line, it will be ZX plus 3Z small n. ZX plus 3Z small n is a zero sequence low voltage side. Similarly, this will be positive side, positive sequence impedance will be how much? Z into X, and this is also Z into X. That means these are two. So we have now two sequence network. We can show these two windings as a two sequence network. First, if we consider the zero sequence network, how it will be? Positive side, that will be, this is one, then this is one, then it is coming over here. This is a VA is 0. We are applying. Current is going, suppose I is 0. It is zero sequence voltage. You are applying on the high voltage side, and then the current is going I is 0. What will be the impedance? This impedance, it is your Z is, and this is 3Zn. That is the high voltage side, zero sequence network. Now if you go to the low voltage side, that will be similar. That will be similar network. That will be ZX 3Zn. Here we are applying Vx0. Current is going Ix0. Right? Now, this two network, we have done the equivalent circuit for the transformers. This phase impedance, we can convert either primary side or secondary side. Similarly, this neutral impedance of both winding we can transfer to the one winding. We know if we want to convert this from the secondary side to the primary side, what we have to do? We have to multiply this impedance into turn ratio A square. That means this primary turn ratio T primary and T secondary, that A square. That is our voltage ratio. You can say primary voltage by secondary voltage A square. We have seen already. So by using this formula, this ZS can be transferred over here. Similarly, these 3 ZN we can transfer over here. That means these two network we can combine together. Then we will get a overall zero sequence network. That how that would be? That will be, this is one phase network, that is equal to how much? ZS plus equivalent of this to the primary side. That means ZX dash, that is the equivalent. Then you have a neutral side impedance, zero sequence impedance, that is a 3ZN, Z capital N plus 3ZN S dash. That means this 3ZN we transfer to this primary side using this formula. So then it is going back. This is here. So then this is your secondary side terminal. And there is a neutral over here. Right? So if we consider this, this is how much? This voltage is a VA is 0. Here voltage is V small a is 0. Or VX0 you can say. So this will be the equivalent network for this star-star transformer. And as this star-star transformer is the same phase sequence, both winding, there is no phase shift between these two. So this way we can represent the transformer equivalent zero sequence network. Then if I go to the positive sequence network, then how much? In the case of positive sequence impedance, this part is 0. So I have a here this two impedance, that is a Z is plus, or here this is a Z is dash X dash, right? This is going over here, and that is your voltage. This is your applying how voltage. You are putting VA is over here, VX1 is over here. That is a positive sequence network. Similarly, Z negative sequence network will be similar. Only here it will be VA is 2, here will be VX2. So this will be the positive negative sequence network. So this way we can determine the positive sequence network, zero sequence network and negative sequence network for the star-star connected transformer. Similarly, if I go to the delta-delta connect transformer, then what will happen? In case of delta and delta connection, both winding is delta. What will be the condition in that case? Let us draw the delta. Suppose this is our delta. In case of delta, what will happen over here? This is a delta, this is a delta. Both are in the corresponding star form like this. So both in the same phase order. Okay. So in case of delta, this Zn is how much? It is a infinite. Zn is infinite. If it is a infinite, then that is open. If it is open, and this winding, suppose this winding impedance, it will be total impedance divided by 3, Z delta by 3, that will be your Z is, you can say. Here also the same way, it will be Z delta, delta Z, you can say Z delta, a small side divided by 3, this side, LB side. So we can find out this is impedance how much. Now here Zn is infinity, so if I put this infinite, then what will happen? This will be this impedance, that will be how much? That will be Z delta by 3. Okay, and both, and similarly this will be another impedance over here, that is a Z, a small z delta by 3, my secondary winding converted to primary. Then here will be open, as it is infinite open, so it will go over here, this is here, and the current will be like this, right? So this will be the, in case of your neutral path will be back like this. Okay, that is a both side is delta. So here also it will be infinite, and it will be connected over here. So this will be the equivalent network for delta delta. Both sides it is infinite. So neutral is not connected. Here also neutral is not connected, open, and this is the impedance of this. That will be the sequence network for that delta delta transformer. Now in case of star delta transformer, this will be slightly different, because star delta transformer, when you are connected, there will be a phase shift between these two. there will be a phase shift. Suppose this is a star winding, okay. Suppose this is a star winding and corresponding delta winding is like this. So if you draw this thing, then automatically there will be a phase shift. So there will be a phase shift of 30 degree. That is for the positive sequence. In the case of positive sequence, there is a positive, positive sequence is similar to the original. Suppose this is the original 2 transformer. Phase, it is a phasor diagram of this. Now if we dissolve this thing into sequence network, 0 sequence, positive sequence and negative sequence. So this will be, there is impedance over here, that is a Z, Y. There will be impedance over here, suppose Z, Y. There is impedance over here, Z, Y. And this is a Zn, okay. And here this is a similar, here is a small Zy, this is a small Zy, and this is a small Zy. This Zy how much? Zy equal to Z delta by 3 here, okay. These are the two transformers, primary, secondary. Now here, if we go to the 0 sequence network, same way, that is a primary side. What will be the 0 sequence network? Primary side will be Zy plus, here will be 3Zn, right? This capital A, 3Zn. Now when we transfer this secondary side impedance to the primary side, first you want to bring one phase 1. Phase 1 will be here, coming over here, Z small y, right, dash. This is coming as a turn ratio with this. Then what is happening over here? Then there is no neutral over here, right? If the neutral is not there, then this is open. Then it is going over here. From here, it is coming back. That is your V0. And the current is going through I0. That means what is happening? 0 sequence network for this star delta transformer. So this impedance ZY plus this one. That means ZY plus ZY dash. That is the one impedance. So we can delete this. This is come like this. And this is a 3Zn. This is a 0 sequence network for this star delta transformer. Now next go to the positive sequence network. In case of positive sequence network, what will happen? Positive sequence network same like before. There is no neutral is not getting connected over here. Only positive sequence network will be there. So the positive sequence network impedance will be, there will be one impedance, that is a ZY primary side plus ZY dash phase equivalent impedance of the secondary side transferred to the primary. Then on the secondary, it is a delta star transformer. So this positive sequence, there is no 0 sequence issue over here. So this will be, then there is a connection over here. This is a primary and the secondary winding is here, right? This is a mutual coupling between these two. And there is no neutral here. Now this primary and secondary, there is a phase difference. We have seen 30 degree. So 30 degree phase difference means what we can write? J into 30 degree. J30. Okay, J 30 degree means it is a e to the power J30. When a cos 30, you can say e to the power J theta, J 30 degree. That is a phase, it is a cos theta 30 degree phase difference between primary and secondary, which we have shown in the vector diagram. Our vector diagram was like this and delta was like this. So delta voltage over there, this angle is 30 degree. So that is a E J30. So that is the positive sequence. Similarly, if we go to the negative sequence, it will be identical, but here will be angle will be minus J30, because we have seen positive sequence network, for that this position is identical. Vector position of this voltage will be identical to the original vector, original phase vector. But in the case of negative sequence, it will be just opposite. Suppose this is your VB, VB will be coming over here, so it will be rotating by minus J30. That means this diagram will be like this, and delta will be here. So delta vector over here, and this vector is, this angle is a lagging by 30 degree, so it is a minus 30 degree. That will be for the negative sequence impedance for the transformer. Okay, so this is your delta star delta transformer. So these are the three type of transformer. Sequence impedance we discussed. Now we will go to the sequence impedance for the transmission line. That calculation will be slightly different from these three other type of load what we discussed. So let us draw the transmission line first. Suppose there is a three phase 4-wire transmission line. So this first phase, suppose A phase, that is A phase. Suppose there are two impedances I draw over here. This is the second phase, this is a third phase, and this is a neutral. So this is a positive, this is also positive. Suppose it is a V1, it is a V1 dash. It is a V2, it is a V2 dash. It is V3, it is a V3 dash. Okay. And the current is flowing through this. Suppose I1, I2 and I3. We can do this thing. Now, this impedance is this is a transmission line. You know, in the transmission line, there are two types of impedance. One impedance is the self-impedance of this line. It is a phase. Suppose this is the A phase. So A phase, suppose it is a VA. You write down VA, VB, that will be better. VA, VB, VC. This is IA, IB, IC. Okay. That will be, it is a VC dash, VB dash, VA dash. Okay. So it has a self-impedance. That self-impedance we represent by ZAA. And this A phase has a mutual impedance between A phase to B phase and A phase to C phase, right? So that impedance, suppose we can represent by ZAB. There is the impedance between these two lines, that is we call ZAB. Between these two, we have a ZBC, and between A and C, there is a mutual impedance ZCA. We can write down this way. So if we write down this way, so the amount of voltage drop take place in this part, the current is flowing this way, going out. On this process, there will be a voltage drop over here. That voltage drop how much? VA minus VA dash, right? So that is, we can say this is equal to V1, suppose, okay, or VA. That is equal to how much? VA minus VA dash, we can say in this way. So that is equal to the current flowing through this, that is IA, right? IA into how much? The self-impedance of this ZAA, right? Plus the, you know, the mutual impedance develop when the current flowing through the other phase. That means when the B phase current is flowing, then this mutual impedance between these two is developing, for which there is a voltage drop on the A phase. So due to the B phase current, the voltage drop take place in the A phase, that is due to the mutual impedance, that is a ZAB into IB. Similarly, when the C phase current is flowing through this, due to the mutual impedance or induction between this A phase and C phase, there will be voltage drop in the C phase, that is a ZCA, right? These are the three voltage drop on the line A. Similarly, if we go to the B phase, the voltage drop VB minus VB dash, that equal to same way. When current is flowing through the A phase, there will be impedance, mutual impedance between these two. That's why there will be voltage drop over here. So when the current flowing through IA, there will be a voltage drop in the B phase due to the mutual impedance between A and B. Plus, when the current is flowing through the B phase, due to its self-impedance, there will be a voltage drop. Suppose this is a ZBB. Okay, this impedance is a ZBB and this is a ZCC. And similarly, when the current is flowing through the C phase, so there will be, suppose this is a, it is BC, yeah? C phase, there will be a voltage drop due to the mutual impedance between B phase and C phase. How much that will be? That is IC, C phase current, due to the C phase current and mutual induction between these two, B phase and C phase, that is a ZCB or ZBC, you can say. There will be a voltage drop. So this will be the voltage drop equation for the B phase. Similarly, VC minus VC dash, that equal to IA. Similarly, ZAB, ZAC, yeah, because A to C phase, plus IB into ZBC into plus IC into ZCC. This is we are getting. Now, if we put this equation in the matrix form, what we will get? We will get in the matrix form. This is a 1 voltage. Suppose this voltage we say V net voltage, we can say some tag we can give it. Suppose V, we give a tag of what is it? It's a V dash, okay? Or we put a V capital A, yeah? VB and VC. Okay, this is one matrix. VA means VA tag the drop voltage. That equal to, you see here current IA, IB, IC in everywhere. So there will be one unit matrix IA, IB and IC, right? And then here is a, in the IA current has a ZAA, here ZAB, and here IA current is a ZCA. So here we can write down in this way ZAA, right? ZAA, then here ZAB and ZAC, right? First. Second is a ZAB, this is a ZAB, then ZBB and ZBC, right? Third one is a ZAC, ZBC and ZCC. This is one matrix you are getting, right? So if we matrix important, that means this is your, suppose it is a phasor matrix, BP. That is equal to how much? This is the impedance phasor. That is, you see, this is all our phase. It is a self impedance. This is our mutual impedance. This is self impedance. This is mutual impedance. So this is equal to ZP. We can say it is a phase impedance matrix, and this is a phase current impedance matrix. Phase current matrix. So this is similar relation we are getting as we get for the non-rotating equipment. VP equal to ZP into IP. Now from this phasor impedance, phasor voltage, phasor current and phasor impedance, we can develop the sequence impedance. We have seen that formula. What is that formula? We have seen the formula ZP. What is that? How we can get VP means we know VP equal to A into VS, right? Similarly ZP into IP means A into IS. That is a sequence current. We have seen the relation before. So if both sides you multiply by A inverse, then what is happening? That equal to A inverse ZP into A into IS. This is equal to 1. That means sequence voltage matrix equal to this matrix, that is we call it ZS into IS. So sequence voltage drop, that equal to sequence impedance into sequence current. Now if you calculate the ZS from here, what is the ZS? ZS means first you have to multiply this matrix into A. We have seen what is A. A equals to, we have already seen in the previous video 58. What is A? A equals to a one matrix, that equal to 1 1 1 1 1 A square A square. This is the matrix we have got A, right? So if you calculate this using this, if you multiply A matrix with this matrix and then you multiply again A inverse. A inverse means how much? A inverse equal to 1/3 of 1 1 1 1 1. Here is just, it will be interchange. So it will be A square A square. A square A. That is a inverse. If you multiply that A inverse, you will get the ZS matrix. And ZS matrix, what will be the ZS matrix? Then if you do this multiplication, first this Z3 matrix will be multiplied by A matrix, and then that again multiplied by A inverse. And second assumption, these three-phase lines are balanced symmetrical three-phase lines. Balanced line means all the lines, the mutual inductance or mutual impedance between the phases are equal. That means in case of balanced system, ZAB equal to ZBC equal to ZCA and ZAA equal to ZBB equal to ZCC. If the lines are balanced and symmetrically aligned and balanced three-phase lines, in that case this will be the condition. Mutual impedance between any two phases will be equal, and this will also be self-impedance of all the lines will be equal. If we consider this thing, then the Z in S, that will be equal to, this network has no, so it will be self-impedance ZAA plus 2ZAB. If you calculate that, you will get this. Here it is 0, it is 0. It is 0. Second impedance will be ZBB minus ZAB. And third 0 0 0. That will be the sequence impedance will be like this. This is a ZS, means complete ZS will be coming in this form. So from here, this ZS will be how much? This will be the zero sequence impedance we have seen. This is your ZS. So this will be positive sequence impedance will be like this. This will be ZCC minus ZAB. And negative sequence impedance will be like this. If we convert this equation with this, if you calculate ZS is equal to A inverse of ZP into A, you will get the sequence impedance. Three component of the sequence impedance. What is that? Z0, Z1 and Z2. This sequence impedance, that equal to, you will get ZAA plus 2ZAB. Then you will get ZBB minus ZAB and ZCC minus ZAB. This will be the sequence impedance for the transmission line of a balanced symmetrical transmission line. Balanced symmetrical transmission line. From this equation you can see Z0 equal to how much? ZAA plus ZAB. And Z1 is equal to positive sequence impedance equal to ZBB minus ZAB. It is 2ZAB, yeah? And Z2 is equal to ZCC minus ZAB. Now again it is equal, so it will be ZAA. This is also ZAA. Okay, these will be the three sequence impedance. So what will be the corresponding sequence network? Very simple. So we can draw the sequence network for this transmission line. So this is a zero sequence. If we go zero sequence, this is your impedance. What is the magnitude? ZAA plus, this is one impedance. Then you can write down another impedance is a mutual impedance between these two, ZAB 2 times. And then it is coming to V0, current is going through I0. This is your zero sequence impedance for the transmission line. And the positive sequence impedance, how much? That will be ZAA, and then it will be minus ZAB. So it will be reverse direction. ZAB minus. And then it will be reverse direction. It will be V1 and current is going I1. Similarly, this will be ZAA. This will be minus direction connected, ZAB. This is a V2. That will be the sequence impedance for the transmission line. So from this we can calculate Z0, Z1, Z2 for the transmission line. So these various sequence impedance we draw from the various loads, that will be working as a master block for the complete network. For the complete network, these will be acting as a master block. When we will be going for the calculating of the asymmetrical fault current for line to ground fault or line to line fault or double line to ground fault, in each case, we will see the fault current expression will be coming in terms of zero sequence impedance, positive sequence impedance and negative sequence impedance of the complete network. And if that network contains various type of load, we have to calculate first each load sequence network. That means this sequence network will be the master block. Then we will apply the Ohm's law or Thevenin equivalent of the circuit to calculate the equivalent impedance, and from that we can calculate the short circuit current. So this sequence network is very, very important, and this is the master block or fundamental block to calculate the short circuit, asymmetrical short circuit current. So with this master block, using this master block, we will calculate the short circuit current for the three different type of phases, three different type of faults that we will discuss in the next videos. So today's videos for the sequence components, impedance sequence component for the three type of load, that is rotating equipment, transformers and transmission line, is getting closed over here. Then we'll see you in the next video, that means video number 60. And with that I am closing to this video. Thank you very much indeed for looking into these videos and sharing with your friends and others. Thank you very much indeed. Thank you.